Okay, so today we're looking at fundamental theorem part 1. Okay, let's get it out of our system. Everybody look at the camera. Say hi to the people in the Hague. Okay, good, hi. All right, everybody got that done? Angles, pay attention. Okay. So we're recording this so that these guys can see it over in Europe and hopefully not be too far behind when they get back. I wanted to start, because we're looking at part 1 of the theorem today, I thought it would be logical for us to go back and just think about what we learned a couple of days ago in part 2. Okay? In part 2, I said include a diagram. Pretty well everybody got this. We should hopefully be looking at a diagram that looks something like that. Okay? The blue shaded area, how do we represent that? That would be integral from a to b of f at x dx. And how do I calculate it? I evaluate it at, and then? Yeah, I put in a b, I put in an a, I subtract, right? I put a b and an a into what? The antiderivative. That's the only part that you've got to be sure that you specify. This is what the theorem says. This is the fundamental theorem of calculus part 2, okay, which says the integral from a to b of little f at x dx equals big F at b minus big F at a, as long as what? What's the assumption you have to make here?
Big F is an antiderivative.
Good. Big F is an antiderivative of little f. Another way of saying that is the derivative of, there you go. That's kind of an easier way of writing that. The derivative of big F is little f. Okay? Everybody all right with that? Okay. We're going to be going through kind of a lot of stuff today, so I'm going to suggest you might not want to try and take notes because I think I'm going to be going a little fast for you to take notes. You might just want to copy these off of EDU 2.0 tonight, but you're going to want to have some paper with you so you can jot some stuff down. Okay? So let's look at the objectives for today's class. We're going to apply the fundamental theorem of calculus part 1. Let me start by clarifying one thing. Part 1 and part 2 are not universally agreed on. Okay? I called what we did the other day in class part 2 because that's what your book calls it. If I pick a different book, they might reverse them. Some books say that part 1 is part 2 and part 2 is part 1. In the end, it really doesn't matter. It's just a question of semantics. Okay? So what we called part 2 is what your book calls part 2, but one of the homework exercises calls it part 1. It just depends on who you ask. Okay? But we're calling it part 2 to be consistent with your book. So today we're doing what your book calls part 1, which is applying the fundamental theorem of calculus to problems involving the rate of change of an area. So we've got a few things going on here, don't we? Rate of change tends to mean what? Implies slope and therefore derivative. So this is kind of talking about derivatives, isn't it? Area tends to imply what? Integrals. So we're kind of mixing two themes here. Okay? And we're going to be doing that a little bit today. What I hope to accomplish, what I hope that by the end of the class we can all do, is two things. One, how do we just get the right answers? I'm going to show you some problems. I want you to be able to get the right answers. Two, what does it mean? In other words, once we can get these answers, what are the answers actually telling us? Okay? So there's basically sort of two parts to today's lecture. Two things that we're looking for. One is practical considerations, and one is theoretical considerations. The practical considerations are, how do we get the right answer to these problems? Okay, we see a question involving fundamental theorem part 1, how do I get the right answer? And what we're going to see is that there are 4 scenarios. There are 4 situations we need to deal with, and we're going to deal with them separately. 1, 2, 3, 4. And by the end of class, I hope that whichever of those 4 scenarios I throw in front of you, you'll be able to get the right answer. The second part is the theoretical considerations, which means when I get the answer, when I get the right answer, what is it telling me? Okay? What does the right answer actually mean? This is a harder thing, I think. Okay? Up until about 10 years ago, it wasn't really thought of very much in AP Calculus. Until about 10 years ago, really all we cared about was this part, get the right answer. About 8 or 10 years ago, there was a sort of change of theme in the AP course, and they started going more towards understanding what it is that you're doing as opposed to just doing it and getting answers. And so now we see a lot more questions involved in, here's a problem, solve it, so you've still got to be able to do this, but now tell me what it means, okay? There's a third part which I think is even more important. Once I know what it means, why do I care? How does it help me, okay? That part we're going to deal with tomorrow. So today, we're going to basically do two things, I hope, by the end of class. One, when you see problems involving fundamental theorem part 1, we're going to be able to get the right answers to those for the 4 situations that come up. And 2, what is it actually telling us? What do the answers represent? Tomorrow, we're going to look at why do we care? Or perhaps a better way of phrasing that is, how does it help us? What is it going to allow us to do that we couldn't do today? That we couldn't do right now? And we're going to put that off until tomorrow. Okay? So, that's what we're going to be doing. I want to start with a very simple little review just to get you thinking the right way. Okay? Suppose I ask you this question. What is the integral of x cubed, I think it was actually x squared, sorry, of x squared dx? Everybody take a second and jot down your answer to that. Danielle, what'd you get?
1/3 x cubed plus c.
Sorry, I lied. It was a 3. So it's going to be 1/4 x to the 4th plus c. Same deal, yes? Okay. Everybody okay with that? How do we know that he's right? Sure, if I take the derivative of the thing in red, what am I supposed to get? X cubed. In other words, if I take the derivative of this thing, I get back the thing that's inside. Make sense? In other words, this is effectively telling me that derivatives and integrals are sort of what? Behave like inverse operations, insofar as they undo each other, right? Just like if I square a function and square root a function, those are inverses, they undo each other. If I differentiate an integral, they undo each other. Or if I integrate a derivative, they undo each other. Yes? That's going to be sort of important in what we're doing today. I just want to remind everybody of that. Everybody good? Okay. So, we're going to go into a little PowerPoint that I put together. Just because it seemed like a little bit more of a faster and more efficient way to go through this stuff. So, we're looking today at the fundamental theorem of calculus part 1, also known as that which doesn't kill me makes me stronger. You remember the good old days we had? You missed one, and that's the one that was that which doesn't kill me. The fun we had before the exam. Okay, no chairs, no desks, but ultimately it makes us stronger. Okay, you remember the good times we had after the exam, eating the tacos, always good. I had to throw this in because this is such a great quote, and there are so few good quotes in calculus books. But this is my favorite. This is from Ross Finney and George Thomas, a book that they wrote in 1990. And they said in their book, if you were being sent to a desert island and could only take one equation with you, this one might be the one that you would choose. And this is the fundamental theorem of calculus part 1. Okay? It says, basically, if we take the derivative of an integral, then what happens is the upper limit of integration goes into the function and it becomes f at x. That's it. That's fundamental theorem part 1. Okay? Written out a little more fully, looks like that. If f is a continuous function on the closed interval ab, then the function capital F at x, which we're defining as the integral from a to x of f at t dt, has a derivative for every point in this closed interval, and the derivative is the function evaluated at x. Now, if you're like most people, you're looking at that and thinking, okay, I get the words, I can read the words, it doesn't make any sense. Okay? It's a sort of a hard thing to figure out, and that's what we're going to be looking at today, is trying to make sense out of what all of this means. Okay? And we're going to start by just diving right into a couple of questions. Okay? So, fundamental theorem part 1. A few things to notice. First of all, we're taking the derivative of an integral. Everybody see that? Okay? So the fundamental theorem part 1 only works when we're taking the derivative of an integral. Okay? It's important to understand the fundamental theorem of calculus part 1 is very, very important, but it's only important if we apply it in the right situation. Just like the fundamental theorem of calculus part 2 that we just did, very important. Okay? It's a very useful way of evaluating integrals. In fact, another word for the fundamental theorem part 2 is the integral evaluation theorem. It's a great way of evaluating integrals. What does it tell you about tangent lines? Nothing. Okay? It's of no use at all in evaluating tangent lines, so we have to apply it in the right circumstances. So this part 1, deals with the derivative of an integral. Second thing that has to be true in order for us to use this is that we're differentiating with respect to x here, and my upper limit of integration is in x. In other words, the derivative has to match the upper limit of integration. Okay with that? Third thing is that the bottom limit of integration is what? Is it? I think that's a constant, right? It's actually technically called what? That's a parameter, which means, yeah, it's a constant, but it's not like a 6, which is always 6, right? But a is a constant. Okay, it can be whatever constant we want it to be, but it's a constant. This is called a parameter. So the bottom limit of integration has to be a constant. Okay? And what we notice is that if we've got this situation where we've got the derivative of an integral, top limit of integration matches the variable of differentiation, bottom limit of integration is a constant, then the answer is the function evaluated at the top limit of integration is f at x. We get a change of variable here. Okay? F at t goes to f at x. That's it. That's the whole thing. Again, understanding what it means, a little more difficult, but actually doing it, pretty straightforward, I think. Okay? All we do is we say, if we have this situation, if we meet these 3 criterion, then the answer is just f at t with t replaced by x. F at t evaluated at x. Make sense? Let's look at an example. Here we have the derivative of the integral from minus pi to x of cosine t dt. Well, we could do this without using the fundamental theorem of calculus part 1. We could do this the long way. Okay, the way that we would have done this before today. In other words, if you don't know anything about fundamental theorem part 1, when frankly probably you don't yet, what would you do here? Well, if we didn't have that, could we solve this? Yeah, we could solve this, couldn't we? And then once we've solved that, could we not do this part? Should be able to do that, right? If I asked you to solve this, what would you do? What would you do first? Take the antiderivative of cosine t. What is the antiderivative of cosine t line? Sine t? Negative sine t? Positive sine t. Why is it not negative? What's he doing? Why? What are you doing? You're confusing derivatives and integrals, right? We want the antiderivative, which is the function whose derivative is cosine t. The derivative of what is cosine t? Sine t. So my antiderivative is going to be sine t evaluated from x to negative pi. I would get this, right? What would I do next? Put in an x, put in a negative pi, and subtract. Yes? I would get this. What's the sign of negative pi? 0, right? That's just kind of good luck. Okay? We're happy about that. But we're going to see in a minute that it doesn't actually matter. Okay? But it is 0 here, so it cancels out, and we're left with the derivative of sine x. And the derivative of sine x is cosine x. Yeah? So we could do this the long way. We could do this without using the fundamental theorem of calculus part 1. Or we could use the fundamental theorem of calculus part 1. But in using the fundamental theorem, first we got to make sure it meets the criterion. The first criterion was, do we have the derivative of an integral? Yes or no? Yes. The second criterion is the derivative matching the upper limit of integration. Yeah, I think it is. We have an x there, we have an x there. The third criterion is the lower limit of an integration what? Is it a constant? Yes, it is. And so it meets these three criterion, which means we can use part one of the theorem. Part one of the theorem says the answer to this is this function evaluated at x. In other words, cosine x. Notice we get the same answer. Okay? This one took 4 or 5 steps. This one takes no steps. Right? This is very quick, as long as we know that we can apply it. So it's a very, very quick way of doing the same thing. Make sense? By the way, were we just really lucky that this happened to be 0? In other words, what if this wasn't minus pi? What if this was, say, pi over 2? Then this would be what? A 1. Would that screw things up? Why not? Yeah, because we're taking the derivative of it. It doesn't make any difference what we get here as long as it's a constant, because the derivative of every constant is 0. And is this always going to be a constant? Sure, as long as what? As long as the lower limit is a constant, and the lower limit has to be a constant. Yes? So the fact that this was a 0 was sort of nice, but it didn't really matter. It's always going to work out that way. Everybody good? Okay, let's try one. The derivative from 0 to x, 1 over 1 plus t squared dt. Could we do this the long way? What we'd have to do first is anti-differentiate. What's the antiderivative of 1 over 1 plus t squared? Ah, nicely done, Melendez. Nobody in the last class got that. Do you remember that? Liars. Tangent inverse of t. We could do this the long way, right? We could take the inverse, the antiderivative, we could shove it in x, we could shove it in 0, we could subtract, we could take the derivative, and we could bang it down that way. But let's do it the other way. Let's do it using the fundamental theorem. Let's find out, first of all, am I allowed to use the fundamental theorem? It's got to meet the 3 criterion. Is it the derivative of an integral? Yes. Is it being differentiated with respect to the same variable as the upper limit of integration? Yes. Is the lower limit of integration a constant? Yes. So the rule says, and so what do I do? Piece of cake. Right? Very easy. Right? The derivative and the inverse and the integral kind of undo each other. We're left with 1 over 1 plus x squared. It becomes a function of x. Make sense? Okay? Very quick. Remember I told you there were 4 situations we had to deal with? That's number 1. Number 1 is the situation where everything is perfect, where life is just great, right? Where we get exactly what we want. We get the derivative of an integral. We have these things matching up. We have a constant down here. We have an x up here. Life is great. Okay? When we get that, that's situation 1, and we just put the x in. Okay?